Right, Assalamualaikum and hello everyone. So in this session we will discuss on the topic of the analog to digital converter or ADC, which is built inside your 80 mega 328. Right, so we will discuss on ADC. Alright, so the 80 mega if we were to operate an actual or we call it an actual microprocessor board. So ADCs are usually not built inside the chip. So it is usually uh, serve as an external device or peripheral. So which means that if you want to have an ADC inside your microprocessor system, then you will need to buy or select and purchase an external ADC, which this is what we have been doing during those years lah, right? So there is a difference between using built-in ADC and using an external ADC, right? One thing that we have discussed on these built-in peripherals, peripherals means devices which are embedded inside, is that in terms of, or number one is in terms of performance, right? Number one is performance. All right. So if you have an ADC built inside your inside your microprocessor chip, or you call it a single chip microprocessor, right? The thing is it has a fixed performance because it is embedded inside already, right? It is embedded inside, so the performance is typically fixed lah, right? So we have to refer to the performance of the ADC embedded inside your 80 mega 328, and then you want to look at how well the embedded ADC performs. Usually you want to look at in terms of noise, for example, noise. Okay, how well how much noise is being I mean, what is the white noise given out by the ADC, right? To be frank with you all, right, all devices even though they are digital, they do have noises, right? We cannot run away from noises, right? So you have to live with noises. The only thing is that how much noise that you can afford in your system, in your application. Alright. For example, if I think we've touched on this a little bit earlier, you have a digital system. You have a digital system, alright, and you have you call it a mixed signal system, a mixed signal system, right? For example, a digital system would be like your let's say this session lah, where no, I wouldn't say that. Let's say you want to send some image, not image lah, or maybe text, text or numbers, or usually numbers lah, over the line, over the wireless, or over the cable line, or you have another application where um, your system is not totally digital. Digital. For example, like this session, you can hear my voice, you can see my picture, right? So there's the sensor will be there's a camera, right, which which has many pixels, many millions of pixels, and each pixels can capture variations of color, and also the we call it the grayness, or the level of intensity of the color, right? And also you can hear my voice, where you have a microphone inside my computer, and therefore um, you want to convert my analog voice to digital, right? But because any device would come with noises, any electronic device would have noise, so we want to look at, okay, for that device given by the manufacturer, how much noise is given off by that device, right, by that ADC, in this case lah, in our case is ADC, right? we uh, we would want to ideally we want to assume that your digital device doesn't have noise, uh, on that layman level, yes, right? But us as engineers, including you guys, right, we need to uh, know and accept that every sensors, every analogs have noises. So the thing is, how much would you be able to cope, right? So if will you be able to accept if you have if you can listen to my sound, let's say for example with a little bit of hissing sound at the background, something like that, how much would you be able to accept? So this would depend on your, maybe your manufacturer, alright, of your device, or depends on the application. Let's say for example, um, uh, for biomedical application, there is a very low tolerance on noises, so you want as much as possible to have a very ultra low noise, ultra low noise, and therefore uh, alright, is something which is essential, right? Essential, right? So if you have the ADC embedded inside your single chip microprocessor, so the disadvantage is that um, uh, you, the developer or the engineer, has to accept the level of noise which is embedded together, that comes together in one package, in one package. Let's say if you want to do something like a device for um, an X-ray or CT scan, for example, and that CT scan or MRI or X-ray needs an ADC, analog to digital converter, which converts our analog signals to digital, and then you call it um, it is very low in noise, very ultra low noise, you call it ultra low, very super low, ultra is bigger than super, okay, and therefore um, of such ultra low noise specification might not uh, be able to be provided by the ATmega 328, or an ADC which is embedded in ATmega 328. Alright, so you might say that, okay, I can find another microprocessor, single chip microprocessor, maybe ATmega 32, which is bigger, alright, which has also an ADC, but you also need to look again, right, for that microprocessor which has a bigger ADC or bigger specs, right? So you have to look at the noise again. So, and you have to compare, does it fulfill the requirement of the required level of noise for your biomedical device. So which means that it is always not always the best. It is always not always practical to use the built-in the analog to digital converter. But if we were to use external ADC, we would need to interface the external ADC um, via via other mechanisms like you can buy external ADC and still use 80 MHz, but you need to select the external ADC, alright, which has the capability to interact with the 80 mega, right, through communications like I2C or SPI, which we will discuss later in this subject, in this topic. Okay, but assuming that the ADC is already built inside the 80 MHz, which means that it is already connected, right? So the best thing is that the ADC has been connected, alright. So we only read the documentation of how to program it, alright, and what are the specifications. It's like a manual, manual how to use it, how to do some settings on the ADC, right? What's the maximum speed, things like that. Okay, so um, a few things that we need to look on ADC. First is on the uh, right, is the resolution, is the bits resolution, right? How many bits, how many bits is the resolution? Is it 10 bit, or is it an 8 bit, or maybe 12 bit, or maybe 16 bit, or maybe 24 bits, yeah. Up to, I think up to now there is up to 24 bits lah. Okay, but which one is the best, which one is the best? So what does bit resolutions mean, what does bit resolutions mean? So this bit resolution means simply means how detailed, how small your ADC can how small the voltage of your ADC can detect and convert it to the digital value, right? For example, let's try to draw this. Okay, for example, you have a signal, right? Something like this. Okay, um, let's say the signal is an ECG lah. So an ECG, right? So analog signals means that the signals are totally or what do you call it, totally or very rich, and this analog signals are rich in the context of, let's say for example, time. When you say continuous, right, when you say the signal is continuous, alright, which means that there is no points in between, there is no points in between the signal, that there is a gap, there is no points in the signal that there is a gap, right? No chances, no chances at all, no chances at all, right? there is no chances that there is any gap between the signal at all. I mean, clearly. I mean, if you want to zoom in, if you can zoom in time, right? Let's say you can zoom in the time between 1 to 2 seconds, right? So there's the difference will be 1 second. Let's say you want to zoom in, right? 0.5 between 1 and 0.5 seconds. You can zoom in again, right? And then between 0.5, maybe you want to look at between 1 and 1.1. You want to zoom in again, right? So as long as you can zoom in, then it is not continuous. Continuous means that you cannot even you zoom in as much as possible, zoom and zoom 1,000 times, million times possible, there is still no gap between 2 points in the analog signal, which means that it is purely continuous, purely continuous. All right. So um, this is the definition lah, the definition of continuous signal, continuous signal. Okay, so the thing is, when we convert from analog to digital, right, from analog to digital, right, so digital in the terms is that it is digitized, it is discrete, right? So discrete means it is not continuous, discrete, it is not continuous. You can have a gap between points, you can have a gap between the time points. You can also have a gap between voltage points, right? Just now we talked about the continuity of time. You can zoom as much as possible. All right. The same also goes for other measurements of physics. Let's say voltage. In voltage, you can see if you can look, if you have the analog multimeter, the older ones where you have the you call it the deflection of the pins, because this multimeter, the old multimeters, they use the analog coils, the magnetic coils. When you have voltage, the voltage will deflect the magnetic field, and also which will deflect the pins. But the voltage itself, it is also continuous in terms of physics, right? The physics of voltage. Also, that's how we talk about time. So for voltage, it is also continuous, which means that if we were to if we have a voltage, let's say between 0 to 1 volt, you want to zoom, right? You zoom in, right? You want to see some, maybe there's a gap between these two voltage, right? You want to zoom in, so you cannot zoom in, right? Because it is continuous, continuous. You zoom in again between 0, just now 0 to 0.5, and then 0 to 0.1. You zoom in again 0.01. You still cannot see um, any gap between the voltages. It is like continuous. It is continuous. Like when you talk, right? Your voice is continuous. You cannot actually say that between 2 points of time, or between 2 points of sound levels, there is a gap, a gap. So that is continuous. In our analog world, it's totally continuous. It's very, very pure, very continuous. You can zoom in as much as possible the voltage, but or the amplitude, or the amplitude, but you cannot find the gap. But the thing is, when we want to convert, from analog to digital, digital will convert it with the limitation of uh, uh, there's a discretization, discrete. So that it's like the term we use here is sampling. sampling for in terms of time lah, right? Sampling, you call it sampling rate, right? Sampling rate, this in terms of time. All right, that is in terms of time. All right, this is time t, right? But in terms of voltage also, so you call it the uh, you're going to segment. So digital systems will segment your um, your signal into several levels, right? Let's say at the top over here is the maximum voltage, you call it Vmax, for example. The maximum voltage is able to be captured by your ADC, right? So every ADC will define what is the maximum voltage, or you can do some programming. You have to refer to the manual of the ADC, right, to see can you program the maximum voltage to certain levels. This one we will look further into ADC, but now we want to get the concept of the ADC first, right? And over here below is 0 volts. So like we know, right, if we talk about digital, it's all about zeros and ones. Digital is about zeros and 1, right? If 0, that will be 0 volt. All right, if 1, that will be 5 volt. Okay, so this is you call it one level lah, right? One only 0 or 1s, 0 or 1s. But actually we can break down further, right? We can break down further. Let's say for example I can break down this between 0 and 1, right? Some level, something like this, let's say, right, in between, right? I can have something like this, right? So it's not only between 0 and 5, it will be 0 and 2.5 over here lah. So I would say that we call it, if it is 1 bit, this is 1 bit lah, right? 1 bit. So 1 bit means I can represent 1 bit, 1 bit. So the formula is how many levels, how many levels of voltages. So if it is 1 bit, so the formula is you want to look at the question is how many quantization levels, you call it quantization levels, right? So if it is a 1 bit, then it will be 2 to the power of 1, right? Okay, so there will be two quantization levels lah. Alright, if you have 2 bits, 2 bits, right, then the quantization levels would be 2 to the power of 2, then there would be 4, 4. Okay, let's say for example how do we draw this? This would be 1, 2, 3, so not 3 over here. So let's look at 2 to the power of 2, 4 levels. So you can break into 4 levels, 0, 1 over here, right? So let's go over here. Oops, how to undo this? Oh, what's happening? There's a setting, how object snapping, ink to shape, oh, this ink to table. Okay, so this is one level. and then another level. So we have now we have um, 4 levels, 4 levels if it is 2 bits lah. Why 2? Because the lowest level is represented by the digital value 0 0, right? Whereas the next level is represented by the value of digital binary value of 0 1, and then the next one would be 1 0, and then last one would be 1 1, right? So we can see here how the voltage levels on the right is connected to digital values over here over here. So this if it is 4 levels, then let's say this 5 volt let's say this is 5 volt. So 5 divided by we cannot take 5 divided by actually 4. We need to have because the number of levels is not 4 actually if starting from 0, yes it is 4, but if you want to look at we need to have the formula is 2 to the power of n minus 1 so there would be 3 levels so 5 divided by 3 volts, right? So there would be, for example where's my calculator? So 5 divided by 3, there will be 1.6 so this is will be 1.6, sorry, 1.6, and then times 2, this would be 3.3 volts this is in volts, right? So this is 4 bits 4 bits. I mean, sorry, no, this is not 4 bits. So this is 2 bits 2 bits only. So we can see here, so 2 to the power of 2, we have 4 levels including 0, and then if you want to define the you call it the quantization levels between every level, is you take the maximum voltage, right, 5 volt, maximum voltage 5 volt, divide by 2 to the power of n minus 1 3, and then you will get your you call it the resolution lah, right? So which means that, okay, let's say I want I'm doing, let's say 2 bits 2 bits. I have a signal ECG, then I have 2 bits in terms of voltage level the bit resolution, and then I want to look at also sampling rate sampling rate. So what I want to do here is that what I want to say here is that I want to take certain time I want to fix a certain time to read the measurement of voltage. So right, so let's say for example you want to take a temperature of someone who is having a fever, right? So it's not like you want to like continuously read the temperature, right? You, let's say you want to read every 1 hour then the next hour you read again, next hour you read again. So when you plot the graph when you plot the graph, you will see, what you will see is a plot of temperature over 24 hours, but the interval time is 1 hour, so you have 24 points over there, right? So you can see over 24 hours the rise of temperature, right? So you can, and you can monitor lah, right? You have like a signal a graph or signal, and then you can decide, okay, this one is the patient recovering, or is he getting worse for example so sampling rate the term sampling rate over here means what is the interval time and how frequent we read the voltage, right? So let's say I want you can look and in this example. Alright, for example, I want to read every certain time lah. Let's say every according to this line according to this line. So I want to read this. Okay. So after a set with an interval of let's say t t is sampling period, right? The big T is sampling period. Okay, and I will capture the signal lah. Right. So let's try to now capture the actual signal. So what I'm doing here is I'm going to at this point. Okay, see here at this point over here, right? I will capture the value of voltage. So the voltage of the signal at this point over here is here. Right, so I'm putting a big mark, big mark over here. You can see on the screen, big mark over here. And then after the t time or the time the sampling time interval here, now we're going to sample again over here, right? And again next time. Okay, then here another next sampling again after the next sampling period, right? So now I have basically, you can see I have 4 points or 5, let's say, starting from the beginning so 1 2 3 4 5 6 6 points, right? So 1 2 3 4 5 6 points okay here. So now, right, let's say for example your microprocessor has sampled read the voltage at certain time and store that in a store the voltages in the memory, in the RAM or extra memory, right? And now, right, so the question is, does the microprocessor just keep that signal, or you want the microprocessor to plot the signal on a display, right? Because usually when you have a machine, let's say ECG machine, right? Of course you have your electrodes connecting to the machine. So the electrodes will read all the ECG signals to do the amplification, the filtering, and so on and so forth. And then what do you want to do? Do you just connect that to the patient and that's it, the ECG? No, right? So usually you want your signals, you want to see your signals. Because why? Why do doctors want to see the signals? Because you want to make sure that the signal that you get is the ECG, right? You want to make sure that when you connect the cables to your chest, you connect your cables properly, right? If you don't connect your cables properly, or you put the electrodes on the wrong places, you will not get the signal, and therefore your machine will not give you the correct diagnosis of ECG, right? Okay, so the thing is, you always want to display your signal. First, you do analog to digital conversion, right? And then you want to display that. So when you want to display that, you want to draw, right? Let's say you have a screen, right? You have a screen. You want to plot lah, right? Because screen uses pixel systems, right? Pixel systems, and then you want to plot the based on the digital values that you have converted, you have read from the analog signal. So now you have, so those digital values are this are all this you can see this marks over here lah, this marks over here. Okay, just now we talk about time, right? Okay, but if in reality we also need to refer to the bit resolution, right? So when the ADC do the ADC conversion, alright, it has to be specific. Let's say, for example, we already know that we have 4 levels. We have first level is 0 volt, and then the second is 1.6 volt, alright, and the third is 3.5 volt. Sorry, 3.3 volt, right? So which means that the and these voltages will be represented by these values. Let's say 1.6 volt is represented by the value digital value 01. This 3.3 volt is represented by the digital value of 10, and the volt 5 volt is represented by the value 11. Is the digital value, right? So we already know that. So the thing is, what happens if the voltage is not specific on 1.6 volt or 3.5 volt, right? What happens? Like we are seeing now, right? Our signal is not actually is in between. If you look at this, the first point over here, all right, is not actually specific. It's not exactly on 1.6 volt or 3.3 volt, right? We cannot set our ECG signal when you place electrodes, right? So you cannot set it to go on 1.6 or to go on 0 volt, right? Because this is real signal. You cannot expect your baseline voltage for your ECG would be the same as mine, right? So these are analog worlds. It's very, very different, right? So the thing is, what the ADC will do, the ADC will convert it to the nearest voltage level, right? In this case, uh, it will be converted to the value of 01 over here. Let's see here, 01, right? And then if you can see on the second point over here, it will be converted to the nearest, because this is halfway. This will be converted over here, right? Okay, so next point will be it will go to the nearest voltage left, which is 1.6, and also next 1.6, and then again 1.6 and 1.6. So what your microprocessor will store after the ADC conversion is these values. The first one is 01, the second one is 10, right? And then the third one is 01 again, and then 01 and 01 and 01. Right? This is the digital value that your microprocessor will, of course, do the conversion. Analog to digital conversion, it will convert from analog to digital, and then it will go to the nearest voltage level. Then it will store the digital representation lah, right? So okay, it will store first. So it will store first, and then you want to plot it. You want to plot it back. So now comes the challenging part. So now when we plot back, right? So when you plot back, you will connect. You will draw lines between those values, right? So you will connect point by point. So let's connect the first point to the second point. So please observe this. Okay, first point, second point. The first blue to the second blue over here, and then second point to third point over here, and then over here, here. So what you are seeing now, right? What you are seeing now. You are seeing now when you plot back, it is no longer your original signal, right? It's no longer, whereas the actual signal that goes into your analog input of your ADC is actually the ECG signal. But after you digitize that, right, with the sampling rate, with the bit resolution selected, and then when you plot it again, right, you do not get the actual you not get back the actual signal, right? So you can say that this system uh, with the spec of 2 bits resolution and sampling rate of, let's say, um, 2 hertz. Let's say, let's assume 2 hertz. 2 hertz. 2 hertz means sampling of 2 hertz means 2 samples per second, right? 2 hertz. This means that 2 samples per second. So the time is the time interval is 0.5 lah. The t is 0.5, and then 0.5, and then 0.5 lah, and so on. Sampling rate. So the specification of this system 2 bit 2 bit, and with a sampling rate of 2 hertz, right? When you do the plotting, you will not get the actual signal back, right? So this system is wrong. This system, it does not fulfill the requirements to capture an ECG signal, right? So now what we can see here is that if we do not follow certain specifications, this one we will discuss how to determine specifications, right? If you do not follow specifications, then your system will not be able to capture um, uh, your required signals, your desired signals, right? So to do that, you will need to know what's the best bit resolution and what is the best sampling rate, right? Just now we talked about a system with 8-bit resolution, 10-bit resolution, maybe 12, we have 16, we have 22, and also I think the largest would be around 24, right? So 24 bits means how many quantization levels? So uh, let us erase this first. Where's the eraser? No. So let's see, there's this. Okay. Right. So again, how to calculate the number of quantization levels is how many bits? Right. Let's say an 8-bit. If your ADC is an 8-bit, then it would be 2 to the power of 8 lah. Pen. Okay. If you have an 8-bit, then it will be 2 to the power of 8. Then it will be 256 lah. Open up your calculator. And then if it is 16-bit 16-bit, then that would be around 16-bit 65536 65536 655. So you can do this calculation to the power of n, right? If it is 10-bit, that would be 1024, right? If it is 12 bits 12 bits, oops, if it is 12 bits, then you have around 4096 levels of voltages including 0 volt right, including 0 volt. So this means that the more level you have, all right, the higher bit resolution you have, all right, you have a more accurate conversion of voltage, all right, to digital values, right? Because why? Because you are what you're doing is, when you have higher resolutions, higher bit resolutions, you have more voltage levels, which your 5 volt will be break down into more levels. Just now we break down into 4, now you don't break down into 8, then you break down again, right, into 8, and then into 16 levels, then break down again, right? So when you break down again, your nearest voltage would be your converted digital value would be more near to your actual voltage, right? Would be not more near to your actual voltage, right? So which means that if you have a higher bit resolution, then you have a more accurate representation of your signal. Of course, it will never, if you want to plot, if let's say you want to plot original analog signal with a very high bit resolution, ADC converted digitized signal. If you were to plot that, if you were to plot both analog and digital signal on top of each other, right? Roughly you can see that it is almost the same, right? If you look at far, it's almost the same. But when you zoom in, right, you still have errors. But the errors, you can accept that, right? You can accept that. Because why you can accept that? Because it is almost very close to your original ECG signal, right? It's almost very close, right? Even though if you zoom in again, zoom very deeply, you can see some levels, some might not follow the actual analog voltage, because analog voltage are very pure, right? But when you convert to digital will definitely fall somewhere in between those quantization levels, right? So even though you can have a 100 bit ADC, you can have 1000 bit, but between that 1000 bit still have voltage levels, but the voltage levels will be very small, right? Even if you convert even deeper, one trillion bit, 1 million bit, right? So 5 divided by 1 trillion, right? You still have some voltage levels, right? So when you convert to digital, it is already discrete. Voltage are discrete, right? You will never compare totally the same as the analog. But the thing is, how much error, you call it the quantization error lah. The one that we see now, the one we see here in the screen now, here is the result of quantization errors lah, right? So how much do you allow, right? Right. So of course you can have 1 trillion bit, 1000 bit resolution. But the thing is, the more bits you have, you need more memory to store your digitized values, right? Remember here, the more resolution bit you're going to have, the more memory that you're going to need lah. Let's say for example, your memories usually is counted in terms of bytes. Bytes mean 8 bits lah, right? So if your ADC is an 8 bit, alright, so one conversion is stored as 1 byte, right? If your 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 ADC is an 8 bit, so one conversion, it becomes an 8 bit values, alright, and that value is stored as an 8 bit, or stored as a 1 byte. So 1 byte. If your ADC is a 16 bit, right? 16 bit is 2 bytes, right? 2 bytes. So you need 2 bytes to store your resulting values of your ADC for a 16 bit ADC. So just now you're using one, right? One 8 bit ADC, 8 bit resolution ADC. You only need 1 byte, right? But when your conversion is when your resolution is 16 bit, so you need 2 bytes, so you need more memory, right? So if your resolution is 24 bits, right, so you need 4 bytes to store one value, to store one value which represents the voltage, right, of your signal. So you can have many bytes, many bit resolution. You can have as high as possible. So the thing is cost. So when you need more memory, you need to add memory. So memory is cost. And then in terms of technology also, alright. So how capable is the current technology? So let's say technology in 20 years ago is different from technology now, right? So now you can have 24 bits, but 20 years ago, you see mostly at around 16 bits, right? 20 or 40 years ago is up to 20 bits. But as technology progresses, you can have more bits, 24 bits. Maybe in future, maybe next 20 years, you can look at maybe 48 bits, for example. Alright, but that depends on the current technology lah. But again, you can have many bits, bit resolution, but you need more memory to do that. So more memory means more cost, and also when you need to add more memory, you also need to have, expand your space lah. Your microprocessor board, you need more space for that. Right, space, physical space, need to put ICs, right? The memory ICs need to include on your boards, right? So yes, so just now we talk about 8 bit and 16 bit. So what about 10 bit? 10 bit is, let's say for ATmega 328, the resolution is 10 bits. The resolution is 10 bits. So the thing is, for here you can see here, 10 bits. So so it is 10 bits. Right, so it is 10 bit ADC. So how many bytes does do you use to store this 10 bits? So if even though it is 10 bits, so you still use 2 bytes. You still use 2 bytes, because why? Because you cannot store as a half a byte. So there's only 1 byte, 2 byte, 3 byte, 4 bytes, and you cannot go in between. So more than 8 bit, you have to go to the next byte. So you need to use the full byte. So which means that for 10 bit, you need 2 bytes. So one conversion for this ATmega, for the ADC built inside the ATmega, you need 2 bytes to store a single conversion of the ADC. Right. And then, so this is the feature of the ADC built inside the ATmega 328. Right. And then we want to look at conversion time. Right. This one reflects to your sampling rate, your sampling rate just now, the time that we the t over here, the sampling rate, right? The t over here. Okay, so the sampling rate is it range from 13 to 260 microseconds conversion time. Right, this is conversion time, the time it takes to convert from the analog, right, from the analog to become digital. Alright, so we can generally we can say that how do I clear this? No, I don't want to clear canvas. I'll clear this first. Let's clear this. Okay. Okay, how to clear this? Oh, I'm not sure. Right, so 260. So sampling rate. The formula for sampling rate. Sampling rate Fs. Fs equals 1 over t, where t is your conversion time lah, right? Or basically the t would mean the time t the time between two conversion, right? Between two to conversion. Just to get clear up, so when you have the first conversion time, this is the timeline. this is the first conversion, right? So we at this point we give instruction to for the ADC to convert from analog to digital. So this is number 1. And then our second conversion time, sorry, let's make it bigger lah. I want to zoom it inside. So our second conversion time, so over here. Okay, but the conversion time in the datasheet that is highlighted just now is 260 microsecond. It's not actually the T over here is this the T over here is this is T, right? But the TC, the T conversion time, TC, might be something just like this only. Alright, might be something here. TC, TC, right? This is TC. TC, this refers to conversion time. So what happens to the remaining time over here, right? So let me shift the second conversion to the end. So what can we have? What can we have in between the conversions? In between conversions of the analog to digital. So we can have conversion time. We can have some other processes like writing to the RAM, right? Write to the RAM, because you can convert, and then you want to take the converted value, the digital value, you want to store in the RAM. So that's one process, right? If we do programming, so that will consume time also. It will consume clock cycles, clock cycles. So there's a time over there, time to write, right? And also maybe if you want to do maybe real time, right? You want to do real time plotting, and then maybe you want to send data to the display, send data. So you might have another time frame which include time to send data. Alright, time to send data, right? And then maybe you have another time slot to actually plot. You need time to plot. So all this time, right? All this time over here will total all together, right? And then you will get your resulting T over here, T. And then here you can actually define your sampling rate, your sampling rate, right? So you not only convert and you not only store, write, and then you want to maybe if you have a real time system to plot signals. So you send, right? You have time to send from your microprocessor board to the display board, and then maybe the display board needs time to plot, and then another time, and then that's why you have your total time over here lah, right? So that T over here. So if the conversion time over here is in the datasheet does not include the everything yet, so you need to consider other processing times also. But let's say you don't need to plot, right? Let's say you don't need to plot, so you cancel out plot. You don't need to send data outside the board, so you can cancel out that time, right? You only need to write to the SRAM, right? And writing to the SRAM usually is much more faster lah. Let's say it will consume maybe 1 microsecond, for example, 1 microsecond. So your T will be let's see the fastest rate of conversion time. The fastest rate is stated here is 13 microsecond, and the slowest is 260 microsecond. So you can take let's say the fastest would be 13 microseconds plus 1 microsecond to write to the memory SRAM. So that would be 14 microseconds. So what you want to take here now is 1 over t, which is 1 over 14 1 over 14 microseconds. So you can say your maximum sampling rate, right? Maximum sampling rate. So let's open up the calculator. 1 over 14 microseconds. So 1 divided by 14 micro, 0, 0, 0. 14 micro, this is milli, 0, 14 micro, 1, 4. So your sampling rate would be 71, 71.428. 71.428. So it's around, so your sampling rate would be 71.48. Sorry, 71.48. 71.428. Right? Point here means kilo lah kan. So kilo samples per second. You can represent your sample rate as hertz, Hz, or also KSPS, samples per second. I would prefer KSPS. KSPS. So if you see hertz, it's also acceptable lah. Right, but in the datasheet, it says up to 76.9. So 76.9, maybe they take 13. So let's try 13. 1 divided by 0.000013. Yes. So let's maybe the time to convert is already included in also storing, but who knows, you might have your own processors that you want to add, so just add 1 microseconds. So the maximum you can go is up to 71 kilo samples per second, or if you want to go tight into 13 microseconds, you can get a maximum of here 76.9 kilo samples per second, or even up to 15 kilo samples. So 79 and 15 is lower lah. Right, so this is assuming maybe 76 kilo 9, assuming 8 bit. So if it is 10 bit, you need more time to store, maybe store. So that's why if you go maximum resolution at 10 bits, so your sample rate goes much more lower lah. In this case 15, right? Because you need the processor need times to store and then convert again and then store again, right? So you get 15 kilos per second. So the point up to this, so the most important point lah for ADC is one, bit resolution. Second is on the sampling rate. So I will end this session up to now. Alright, that will cover the overall understanding on the ADC lah, right? The ADC. So in the next session, we will discuss of how to do the settings, to do the settings for the ATmega to actually activate the ADC. Right, we will look at registers. We will look at the protocols to start the ADC, and the registers involved that we need to write and read to and from the registers, and also some examples. So we will do that in the next session. Alright, so this is a recorded session offline. Alright. I cannot do it online because the system is very slow. The line is very slow. I want good quality, no lagging for the recording, so hence I do offline recording. right? So bear with us during these pandemic times. So all the best to you. All right, and see you in the next session.